Wow. All right. Welcome everyone to this second summer reading group. We are discussing seed, wiki SQL, text to SQL, SQL to text, all manner of things extending off of our previous discussion from transformers. Aaron will be your presenter today. So we will go through the slides of the work that we've done. And if you need to interject with questions, please do. Otherwise, hold the questions to the end and we'll have time at the end for questions there as well. All right, so thank you very much everyone again for coming. And I will turn this over to Aaron.
Great, thanks, Ian. For those that haven't met me, my name is Aaron. I'm an ML intern working with Ian for the summer. And this is a bit of a culmination of the work I've been doing since our last presentation on transformers. And today we'll be mostly talking about how we've extended the use of transformers into generating SQL queries from English and vice versa. So a brief kind of agenda of what we'll be going through today. We have three main points. The first is going to be English to SQL. So the motivation for doing so, prior work that's been done in the space, in academia mostly, and our model and the models that we use and the data that we use to train our model for this SQL generation. Next, we'll talk about going the reverse direction, SQL to English. So introduction into that task, maybe why we're going with this task, which leads into our motivation, and again, our model for this task. Finally, we'll be talking about again, what's next steps, and then we'll end with a Q&A to conclude the presentation. So before we begin, I do want to start off with kind of a last time where we left off. So last time we talked about transformers, right, as this new architecture for neural networks that allowed for parallel processing, long-term memory, and improved performance for NLP tasks, right? And so it's powered by this idea of this self-attention, right? So given some input sequence for each token, you're looking at which other tokens are important for the meaning of this current token. Don't worry, we won't be going over that again. It was pretty technical. Today will be pretty hands-on. And the question we kind of left off with was, how can we build some product that harnesses the power, the predictive power of these transformers? And so we're building off of that question today. And that's is what my work has been based on the past few months. Great, so we'll begin with going from English to SQL. So great, task overview. So we noticed that, is this loading here? We noticed that there's an untapped potential in the data catalog for non-technical business users. They have some difficulty in using the data catalog if you don't understand SQL, or you're going to need a data analyst to use the data catalog to its maximum kind of efficiency, right? And so we want to have some way for these non-technical business users to ask questions in natural language, but put SQL into the table that they're looking at. And so text to SQL is this concept of generating SQL queries from natural language, right? I think that's pretty intuitive, text to SQL, right? And it should be noted that, I'm not sure why it keeps sort of reverting there, I apologize. That's an open field of research in academia, and it has been for several years now. And it's really exploded due to this, again, use of transformers. And so just for kind of clarity, here is a, this is an input-output sequence for what this would look like. So you'd input maybe this text, what school did Williams go to, and the model would return this SQL query. So very cool stuff. How can we kind of do this? Let's get an introduction and background into what's already been done. So the kind of flagship data set that's used for this task is called wiki SQL. And so wiki SQL is this huge, contains 80,000 samples, semantic parsing data set, and it's been scraped from, extracted from the web, Wikipedia, and it covers majority select and where clauses, so pretty basic SQL queries. Academia used for training and then testing to see how well their model performs. And this is an example of some of the question query pairs within the WikiSQL dataset. And again, this is public, of course. So accuracy metrics for this task is called logical match accuracy and execution accuracy. So LM accuracy is seeing if so you have a model and you're producing some output, which is your SQL query. And then you compare your predicted query with the expected query. And by comparing those two strings, if they're the same, you +1. And if they're not the same, then you don't add anything. And then the number of queries that are exactly the same or have the same meaning, that is your accuracy. Execution accuracy is whether or not the output is the same. So if you were to run the SQL query on this table, does it produce the same output as the ground truth query? Okay, and so both these are important. They're a little bit different for measuring the performance of your model. Finally, we should note that there are two main strategies for this type of task. So we're talking about right now using transformers, the seek-to-seek language modeling, which mainly consists of just having this transformer model, putting an English question in, and it just spits out SQL, right? Seems very easy, very intuitive. Here's an example of a seek-to-seek model. This is going from French to English, but you can imagine it's going from English to SQL. The second one, slot filling, is something that we won't be covering today, but I do want to mention it as this is where most of the higher accuracy scores in academia in this field are coming from, using these models, slot filling. And the idea is that within the WikiSQL dataset, every query can be kind of broken down into this syntactical structure. We have some select and an aggregator, and then a specific column where, and then some conditional column, operator, conditional value, and so on and so forth for this syntactical skeleton. And basically, for this slot filling strategy, what they have is basically, again, the skeleton for the syntax. So you only, instead of having to produce the entire query from a transformer, so which will have to learn English and then we'll have to learn SQL and then translate that, you instead have maybe a multi-layer perceptron for this aggregator, and it will learn, okay, what aggregators are there? So there's count, there's min, max, average, right? And so we've limited the output space for this aggregator function, and it needs to predict, out of the 4, which one it is, or none, right? So I guess 5. But that makes it a lot easier for the model, right? Because it only has 5 that it needs to predict out of a, pretty much infinite output space if you're just having to learn a SQL syntax, from scratch, if you had a transformer, right? And so, a specific column, for example, would go next after this aggregator, right? And so there are only a finite number of columns, right? So you can give this model the columns, and it'll have to choose from these columns, right? So you're defining the output space into a finite, finite space. We will not be covering that today, and we did not attempt this approach. And the reasoning for this is because these models, although they have state-of-the-art accuracies and performance on WikiSQL, that's kind of the issue, right? WikiSQL's queries are relatively basic and are not fit for professional use in industry, right? And so these models are really just overfitting to the WikiSQL syntax, right? So it's not readily available for everybody, right? It would perform poorly on real life queries, predicting real life queries. And so we want a more generalized transformer model, language model that's able to actually learn English, learn SQL, and perform that translation, right? So that's kind of the goal for this task. So let's now talk about our approach and what we've done for this task. So we are using a model architecture known as T5, text-to-text transformer. And this was published by Google less than a few years ago. And what it is it's a very general transfer learning transformer architecture that allows for a variety of seek-to-seek tasks, right? And what's great is that we can fine-tune T5 for English to SQL, right? So in the original paper, it came with preloaded English to German, English to French, things like this. But we can fine tune that model because it's already learned English. It just now needs to output some SQL. So we can give it some flavor of SQL and train for a little bit, fine tune it. And so now it learns SQL and is now able to output SQL. So that's pretty well known already in academic work and has been done. And in fact, there's this library, NLP library called Hugging Face, which already has this model, pre-trained T5, right? You can imagine, training a T5 from scratch is very expensive. It will take a lot of time. This one is already pre-trained, and also has already been fine-tuned on WikiSQL, right? And so our goal is to try to mimic or best approach similar results seen in academia for this task. See if it actually works. Can we actually go from text to SQL, right? And so we're going to use this model, T5, fine-tuned on the WikiSQL dataset and find out. It should also be noted that we used Google Colab. So, all the training and inferencing is free. So it's really interesting with all these constraints and very minimal number of kind of requirements where I want to see how far we can get. Okay. So with this in mind, let's kind of dive into our code here in the Colab and see how we made this model and how well this model performs. So, okay. Can everybody see this? Take that as a yes. Great. Cool. So I won't distract us with all the kind of small nitpicky details in the code, but I'll kind of walk us through the process of what this looks like using Hugging Face, seeing how simple it is, and seeing the results that we get from such very relatively easy pipeline. So we can install our dependencies and set the seed, which just makes sure that any randomization is set. So this can be reproduced. This is how we're grabbing the data from a datasets library, also created by Hugging Face. So again, because WikiSQL is a baseline dataset for this task, we can, it's open source, we can download it. So once we've downloaded it, we can look at, what one of the samples looks like. And so here's what one of the samples looks like. So we have a question here, what is Terrence Ross' nationality? And then we have the SQL, right? So we have the human readable SQL, as well as the conditions and indexes for the columns. And then we have some information about the actual table, right? So the player, nationality, and these can be useful for what we talked about, the slot filling strategy, right? Because it needs to know which columns to choose from in this finite space and then choose one. But we don't really need all this information, right? Because we only care about translating from English straight to SQL, right? So we need to scrape some of the JSON and only grab out the human readable SQL as well as the question associated with it. And then here we can shuffle it. And then this is what we get. So we look at the first three questions in SQL and question SQL pairs. We see, here's the question. And this is the SQL associated with it. And these are just the first three. And these are the table IDs. So we can use these tables. We can take these predicted queries, run them on their corresponding tables and see how well they do, right? Do they actually produce the same output as the ground truth label? or not. So we can calculate some execution accuracy there. Okay. And this is how we're loading in our model in our tokenizer. Very easy. Again, we're just loading it in from Hugging Face, which is a pretty well-known library for an NLP, which has already been fine-tuned on WikiSQL. And we also have our tokenizer, also pulled in from Hugging Face. This would be our model architecture, just to make sure that we've loaded the correct model, which we have. This is our loss helper function for loss, which allows us to generate the loss and see how well we do. We can come back to that if we need to. I think that's not as important, as well as a helper function for generating queries. But I think probably what we all care about is, after all this, model, how do we do, right? So you can see here that I've run this model, this fine-tuned model on the first 100 samples within our test set, right? See how well it's doing. And as you can see, and I generate the execution accuracy and logistical match accuracy here. And I know it's quite hard to see, but we have some copy and paste, or rather screenshot examples here. So here's an example where the model predicts correctly, right? It actually predicts the exact query that was expected, right? It's like count season from the specific table where the driver equals Clay Regazzoni, right? We also noticed that there are some close calls where it doesn't quite get there. It's really close, but it's not quite there, right? So here's an example from the 57th iteration. Select the sport from this table where the score in the final is 3-2, right? It's very close, but actually the expected where the final score is 3-2, right? And so the issue here is that the score in the final is not a column, right? And so that'll produce an error in output. So that would be incorrect. And then same thing for here, this another close case. Here, the predicted was original air date when the expected was original air date without the space. When we would even argue that the predicted should be more correct, grammatically, but again, it's not a column name, right? So that'll throw an error at you. And here's a failure case of where it just doesn't really work. It's here, it's missing the aggregator, and Lee Jansen, isn't probably not a very well used token within its English dictionary, the model's tokenizer. So it wasn't able to predict that. So this gives us a final execution accuracy of 43%. If you run it for longer, we actually get an execution accuracy closer to 50%, which is not bad, right? They're executing 50% of the time, and it's they're very close, right? And so there are some initial takeaways.
Sorry, real quick, Aaron.
Sure.
When you say execution accuracy, are you just saying that it produces SQL that is able to execute, or that upon execution gets back the sort of correct response, or the response that matches the ground truth?
Right. So for this, so here what I've printed is the executable, actually, just whether it executes. So this is executable, like just whether it produced good SQL, right?
Yep.
And this same output accuracy can be thought as the
Gotcha. Okay.
we talked about earlier. And what I'm saying is what kind of hits to 50% is this executable accuracy, right?
Because what's interesting to me is that the 33%. So that's great. That means a third of the time I type in English and I get the right answer.
Right.
The delta there, that 10% where it executes but the answer is wrong, that's actually the most worrying part in my mind, because it's like it looks like it worked, but then because it's syntactically good enough but semantically incorrect translation that I might get the wrong result. But anyway, keep going. I'm following now. Thank you.
Yeah. No, that's a great point, right? So like you can imagine that if we had deployed this, right, and we have like something that flags just to make sure, like, oh, let's not return syntax query if it's not syntactically correct. well, sometimes it will be syntactically correct, but won't produce the answer that you're looking for. And so that's kind of dangerous. And that's something that definitely we're going to talk about after. But that's a really good point. And so, yeah, thank you for that. Back to the error analysis. There are some things that we can notice here. Like, one is that the model has learned English really well, right? And thus, like, for example, here, it's using synonyms, right? For example, here it's where the position equals T3, when it should have been where the place is T3. When you can argue position and place are very similar words, right? At least, in its embedding space, they're very similar. And so, this is without kind of overfitting to the solution to the test to the data set, or by changing the architecture firmly, closing the output space so that you can only choose from the column names, right? And so that's a very interesting issue that we ran into. And if we go back to the slides here, if it'll let me, we have some other kind of takeaways here. That's the following, right? So first is that using the pre-trained model from Hugging Face is really straightforward, right? Wasn't I didn't have to build an entire debugging pipeline or go through iterations for the DL architecture that you would normally go through. So that was great, and we could actually replicate existing results from academia, which again is really awesome. Second takeaway is that it's really difficult to generate SQL, right? Syntactically perfect SQL and SQL that is like meaningfully correct, right? That you're getting the same output as you're intended to. So that's another point that we'll bring up later. And the third thing is that the WikiSQL data set is great for academia, but it's not very useful for, as we touched on earlier, it's not very useful for industry use. I'm sure many of you have written much longer SQL queries than the queries shown in the WikiSQL data set. And so we can imagine that the model would, if trained on WikiSQL, would start to break down as you ask longer, more complex questions, and it probably just wouldn't be able to generate longer output queries. So that's an issue, right? We're missing a lot of the functions, methods that are required for long SQL queries like joins, group bys, and order bys. And you can imagine order bys are really important. And so these are three interesting takeaways, the two of which are issues. Okay, so one, it's hard to generate perfectly syntactically correct SQL, and two, WikiSQL is not the best data set. It's a little too easy, right? So how can we kind of fix this, right? How can we fix these issues? So we can start with the third one, and that's by introducing seed. So last time we met was actually on June 1st, and we talked about transformers. This data set actually came out, hadn't even been out at that time, which kind of shows the kind of transforming landscape of NLP. This data set came out in mid-June. So the seed data set is comprised of 12,000 SQL queries. And what's great about this is that it's much more realistic than WikiSQL, as these query description queries pairs have been scraped from Stack Exchange and from users, building actual queries. And so that's really important. Here's an example on the right-hand side, which you can see it's starkly different from the queries in WikiSQL. Another interesting point to make is that because it's a completely new data set, there's actually no research on this. And although that's the case, it should be noted that the authors of Seed that scraped Stack Exchange to create to grab these queries did try to use models that have worked on WikiSQL very well, things with very high accuracy scores. For example, they tried running T5 large. So T5 large is like a larger version of T5. It reaches an execution match accuracy. So the same exact output, 63% on data sets similar to WikiSQL, so 63%. But on this data set that's more realistic, it's probably much more difficult, could only receive an execution match accuracy of 48%. And so that's very different, right? That's very interesting, right? So it seems that the models that have been used in academia and have been reached state of the art are very overfit to the problem and are not realistic for everyday use, right? So that's how we're going to fix that third problem. The second problem, third bullet point here, to use this new dataset seed, which came out very recently on June 9th. And the first point with the difficult to generate perfect SQL leads us to kind of our next task, which is to instead translate SQL to English, right? And so we have this new task where we want to instead of going from English to SQL, we want to generate detailed descriptions for SQL queries using the seed data set, right? And the rationale for this is it can actually be quite useful, right? Many SQL queries aren't labeled in the data catalog, and so it'd be very unhelpful for not only non-technical users, but these long queries that aren't annotated, and so you don't want multiple analysts writing out the same queries for the same question, right? And the basis for this again is that it'll probably be much easier to generate English than it is perfect SQL queries that go through a compiler, right? And so that's really important. And so let's kind of take a journey through what we've been doing with this task. So here's our next collab. All right, that's fine. I have it pulled up here. Great. Okay. All right, so great. We can skip some of this. So again, we have environment preparation here, initial data loading. Sorry, we meant to minimize some of these just because it's a lot of code. So again, our task is to go from these long SQL queries to these easy to read English descriptions, right? And so here's a look at some of the data that we're working with. And what we want to do is filter out the descriptions and SQL pairs from the data. Probably don't need to look at that. Here's an example of what the data looks like. So this is what one of the queries looks like. Select the row number. You can tell it's very long. We have an order by here. And then the expected output would be this description: Uber employees on Stack Overflow by reputation. Okay, we have 10,000 total samples in the training set. Again, we can load this model. This time, this is a fine-tuned WikiSQL T5 going from SQL to English, which someone had fine-tuned. And so we're taking this. This will basically give us a boost to get us training and having our model understand SQL. Okay. We load in our tokenizer as before. And so if we look at this, we look at the, before we actually train the model or fine tune it at all ourselves, which we will because we have a new data set seed, right? We want to look at how well it's doing, how well the model is performing before we train it on seed, right? So if we look at this, our question is the, let me just make sure here. It should be the example input, which was from earlier. So we're taking in this SQL, right? And we're trying to output a description. And this pre-trained model generates this as our description, right? It should be noted that it generates 3 because our model uses beam search and returns the top 3 possible descriptions. As you can see, this is not good, right? This is not really English. They're basically just excerpts of the query, the original query. So it's not very good, right? So what we want to do is we want to train this model on our seed. And so we haven't actually done that before. So what we tried to do is overfit on one example to make sure that it was learning something. And we did that and trained well. So when we train for real, this is what it looks like. Very simple, right? This trainer module allows for us to train a Hugging Face model with our own custom data set. And then we can save our model and see how well it does during evaluation. And so this really emphasizes the simplicity of developing these models now, and using a custom data set to perform downstream tasks, such as going from these descriptions. And this is just the training loss through the steps. So let's look at evaluation now. Right, that's what we really care about. How well does this model do? Okay. So if we scroll to the top here, environmental information, data loading, data manipulation. Again, we're loading in the model to see how well it does. This time we're loading the trained model, right? Loading the tokenizer. And again, we have this, just to kind of remind you all, this was the original example that we tried on the pre-trained model before, when it was fine-tuned but not trained, right? Pre-trained. So this was the query. This is the ground truth label. And if we recall, the pre-trained model did quite poorly, right? It didn't really generate any description for us. Well, after training for a very small amount of time, we see that the generated model, our model generated quite a good description, right? Top Uber users by reputation, right? Really good, right? That's incredible. That's pretty much what we were looking for, right? We're looking for Uber employees on Stack Overflow by reputation, right? Top Uber users by reputation. So really good, right? Well, let's look at some other examples, and we can look at these examples from AAA. So we have this query here, and we want to know, can you describe this for us?
Sorry, Aaron.
Sure.
Quick question there. So, what do we know about the data set here? Is this idea that it's all Stack Overflow corporate users?
No, so these aren't corporate users, at least.
Because what I'm trying to figure out is the substitution of users for employees in context, is that semantics preserving because a user of Stack Overflow is an employee of something? Or do we actually, instead of counting Uber employees, we're now counting, you can imagine that there's maybe a 10,000 Uber users for every employee if we actually had like a table of people in the world.
Right. So, so I guess what you're saying is that, I guess semantically, this isn't the same as what was generated, right?
I mean, just in English, it's not, but in the
Right.
context of a certain table, and I don't even know if there is a concept of a table in your model here, but it could be equivalent. But,
right.
but in just plain English, it's not, right?
In plain English, it's not, right. And it's not, I guess, I guess the ground truth is not the same as generated. If we look at the meaning. Here, what's incredible, however, is that we've trained a model that, went from, just producing
Gibberish, right? To something that reads English.
That's
sure.
In English and is relatively close to the meaning, and it's able to scrape out.
I guess one question here is, this array, what is the second term there, the top Stack Overflow users by reputation? Because those two together actually do seem to be a match. I just don't quite know what I'm seeing there.
Yeah, so the underlying data here, just to refresh what Seed is talking about, is the Stack Overflow data explorer data set. So
Gotcha.
these are people running queries about data that Stack Overflow has about its own users. So you're correct. It is linguistically ambiguous whether or not an Uber user is someone who uses Stack Overflow a lot. Is it an employee of Uber? Is it just a random person who uses Uber and happens to be on Stack Overflow? But at least one of those valid interpretations is someone on Stack Overflow who is also from Uber.
And the Stack Overflow you get for free because of the data context. Yeah. So
exactly.
That's very helpful. Thank you. And absolutely, Aaron, in that context, that it seems much more accurate. The one other thing real quick is just, again, which is generated, and there's this array there. What is, you read kind of up to the first comma. What are the other two? Are those like alternative, like next best renderings, or?
Right. Yeah. So this T5 uses beam search, which I guess, very quickly memorizes the top three, or the top n number of closest predictions that it can make.
Okay, so that last parameter there equals 3. It'll just do that many, and you were reading the top one.
Right. Yeah. So I was just reading the top one. So you can imagine this is useful if maybe the first one doesn't make sense. We can give multiple.
Yeah. I think if you gave me those top 2 at least, right? Suddenly, it's really very close to the question. And I guess one last quick question. We can move on. Sorry to go deep on this, but do you have a hypothesis for why it kind of couldn't tolerate both Uber and Stack Overflow existing in the same English rendering? Is that just because in the language model, typically the descriptors are shorter, or what do you think that's about?
Yeah, well, it's interesting. If you look at the query, it doesn't even use the word Stack Overflow, right?
Right. The from users and the Stack Overflow is just in the ether, maybe because of the question queries.
So yeah, right. So it's probably so I think the reason that the top one doesn't include Stack Overflow is because it's not anywhere in the query that we've given it. However, you'll notice that it's in the second one. And the reason for this is probably because, well, it's trained on seed, right? And so the entire environment around, or kind of, it's gained some Stack Overflow bias, basically.
Yeah, it's almost like Stack Overflow in this corpus is like the word, of or something, right?
Right,
it occurs
exactly.
so frequently and seemingly randomly because of that's interesting. Okay, I think I get it now. Thanks. Keep going. And I didn't mean to. It's obviously a huge improvement in interpretability from before the training. So I didn't mean to cast out. Yeah.
No worries. Yeah, those are great questions, and hopefully that's clear for everybody else too, because that makes a lot of sense. So yeah, we provide 3 query, or more than 3. Here's an example of a really complex query that we've gone from AAA. And it generates this wonderful description, right? Users with the most recent visits in a month, right? And here we notice that there are a few issues. If you notice that there's an error that's thrown, but it continues, more of a warning, that the maximum sequence length for this model is 512, which basically says that we can only input queries with a certain length, right? And that's inherent to the model itself, T5, not really something that we can change. So that's definitely something that we can improve on, and we'll definitely talk about in the discussions, but kind of a limitation with using a pre-trained T5 model, right? So because of that, the query that's given to the model is actually truncated, and so it won't include some amount of this, which is interesting, and is definitely a barrier.
Sorry, just real quick, constant customer. Can you scroll to where the expected translation would be?
I actually don't think we have an expected.
It's so the top of this cell is the name of the query. So it's customer monthly usage, and if you want to open that query directly, we can take a look at the actual list.
Oh yeah, let me just see here. So
it's something I recently wrote. It's just like over the last, over a given time frame, what was the monthly usage of Alation in that? various customers, all of our customers, I guess.
Okay, so got it. So basically, it's just missing the column for customer, but it actually is a question about users. It's not like saying which customers have the most usage, and yeah, that's impressive.
Yeah.
I'm just looking there. Yeah, I see now. Okay, cool.
Yeah. So it does a pretty good job, right? And so we can look at another example as well. So search display metrics. I'm not sure, Ian, if you want to take this one, because I don't remember what this one's really about.
Yeah, I mean, this is a very accurate description. It is the number of clicks per impression that have at least one click. Like, this is pretty much spot on. If we look at the description, it's the concept of how many of the results that we vended were used, and for the ones that were used, how many times were they used. So the description is pretty damn good.
And it's not getting the comment there. It's
I was about to ask.
It is.
Sorry.
That's the thing,
Yeah.
right? So that's the thing to notice here is it is literally copying the comment out of this query. And as far as I know, like, that is the right thing to do if you were fed an arbitrary SQL clause that has a human annotation in it. I actually like this behavior, but that's the main point here.
Gotcha. So it's learned basically that the ... isn't really a comment; it's a translation as a general rule, without being, there's no regex for that. It just kind of
exactly. And you'll notice that it ignores the first. Like, we have two queries in this input, and it's ignored the first one, and it has said, "Oh, I have the answer, so I'm just going to read that back to the user." So it's both a unexpected success through a novel mechanism and a failure because it hasn't said, "Oh, I don't know how to answer this first query. I haven't given you a summary of both. I've just read."
Right. It's like a good student who knows how to skim, right?
Exactly. Yeah, which was unexpected. And one thing about these out of distribution AAA examples is that I really just went to the first results page of queries in AAA and started like randomly sampling. So this is sort of raw.
Yeah.
We want to go on to real. Yeah. So this one I didn't actually know whether, and Andrea, maybe you can help out here. Like, is this an accurate description? Like, GADB recent sync time for summary view, saying a most recent sync time for a query, is that even helpful? Like, is one of these three good?
I think the third one is probably the best, because query is, like, I think, misleading, because query is a part of it, but like definitely not the main one. And so you could say, like, oh, specific model. Like, if I were to say this, it does say for, it doesn't even say models, but if it could pick out like that model name was important, because it has a lot of cases on that. Like, that would be positive, as opposed to this query, which I think is maybe being pulled out from a specific model name.
I think
I'm not entirely sure where query is coming from.
Yeah, I think that we have a vocabulary because of this these are out of distribution test samples. Yeah. We have a vocabulary that we expect, things like customer and GIDP, these other words, models that might be more appropriate. Whereas the combination of WikiSQL data and seed data, which it has been exposed to, it's more likely to have seen query and other languages.
Yeah, but I mean, it definitely is the most recent sync time.
Okay.
For various reasons,
and then you have that one I didn't evaluate well, so we've got let's go down to the full-on failure case just to. Right, so here's an example of a full-on failure where The question is, who is the CSM AESE, right? This is backing one of our query forms, and it is reverting to that behavior that we saw in the pre-trained state of just outputting portions of the input SQL. So we definitely have hard failures on occasion.
And we would assume that this could be ironed out if it had trained longer, or for example, if we had trained it on maybe not the seed data set, but some query descriptions pairs from AAA or something like this, it would be less indecisive, right? It would have learned longer, learned more appropriate distributions, for example, the vocab distribution.
Totally. You know what's funny though is I know I'm supposed to come in here as a failed academic, but I can't turn off the pragmatic part of my brain. It would be so easy to simply suppress showing the suggested translation if you encounter an underscore or letters on each side of a period, which is like the most basic regex, right? To get rid of this case. I'm actually much more afraid of the case where it seems good, but it's wrong. And then a user draws an incorrect interpretation. So just depending whether you have the academic or the product building hat on, levels of failure and success definitely differ. Just the food for thought.
And one thing that we haven't described here is beam search is a probabilistic confidence-based search, right? It's it has a certain beam width. And so it will always return something regardless of its confidence levels. So it will give you the top three, even if the top three it has low confidence in. And we have not exposed any confidence. We have not exposed probabilities for any of these options.
Yeah, that could be fun further work to see whether the things that look like failures are low confidence. That'd be really encouraging if it's that self-aware. Yeah, awesome.
Or if there's a difference between those, useful and accurate and deceiving.
Totally.
Accurate ones. Okay.
Totally right, exactly. Because a low confidence incorrect guess is really harmless. If it's correlated. Yeah, it's cool. All right, you keep going again. This is great stuff.
Great, yeah. So yeah, we'll go back to the slides now and kind of go over some takeaways from this. Great. So actually, before we do that, now we can probably just go to next steps. So some takeaways from what we've kind of shown today. First off, from the seed, we've shown that training and fine tuning on custom data sets is possible. So as we said, their vocab distribution from WikiSQL to seed to AAA are all very different. And so you can imagine that if we had our own custom data set, we aside from something like seed, we could get much better results, right? Second thing is that transfer learning is extremely cost effective, which we'll touch on later in our next steps. But I didn't really spend any money on anything. This was entire hosting environment was done on Google Colab, so that's really interesting. And then finally, probably the most important is that I think we've successfully shown this proof of concept, SQL to English and reverse is definitely possible, and that SQL to English seems to be much more probable use case, definitely has much more possibility or upside for sure, as it's very easy to generate English as opposed to SQL, at least when it wants to generate English and doesn't kind of not know what to do and just return SQL. Right. So what are some next steps, right? So the first thing is definitely rigorous testing and error analysis, really looking at what, I'll just use the seed model for example. There isn't really an accuracy metric yet, right? What constitutes like an incorrect answer, right? If you're outputting English, right? It's not necessarily, it's not trivial. Whereas for SQL, if it doesn't it doesn't execute, then that's too bad. That would definitely count as an accuracy metric. So what can we use to say whether or not a description is good enough? We would also want to flesh out the characterization of deployment. So things like front end or cost per deployment, what that would look like, would definitely need to be fleshed out. And third, which ties into the first step, is model performance. Right, once we're able to define some measurement and test the model, we want to be able to think of ways to improve performance. So there are a few ways that we could do that. For example, like increasing beams for beam search, using our own custom data set. We use a T5 that was already fine-tuned on WikiSQL, which we didn't do that. So it's possible that would harm the model's performance for SQL to description. So we want to do that ourselves and build it up. And these are just a few examples of ways that we could improve the model performance. And with that, that's just about it. I'll open it up to questions. Thank you very much.
Cool.
Great.
No, that's super interesting and very impressive. One question I had is like on kind of the application of it. So if you have a query, how long does it take to run any given query through to see what its title or description should be?
Yeah, so the inference time on T5 on a GPU instance is about 300 milliseconds right now. So it's pretty slow.
Well, I mean, that, I guess it's like, how could, like if it were kind of applied in the context of the product, it might not have a GPU, like, is that prohibitive in terms of like the application of it? Or could it be something that like someone's wrote a query, they're about to do whatever, here, let's suggest a title for you, and we start getting training data to know whether people agree with the titles that.
Yeah, on CPU, it's about 500 milliseconds, and it should be, the reason it's not much faster on GPU is that GPUs are parallelizable. So if you did a batch of 8 or 12 or 32, right, you could do it in about 300 milliseconds at the same time. So it's still sub-second for inference on, because one of the limitations, but at least consistent aspects of this model is that you have a maximum input length, which means that sort of the worst case of runtime for inference. Unless you significantly change how you use it.
Cool.
Manali, I know you came in a little bit late. Did you have any questions that?
No, I joined late. This seems awesome. I guess my product brain is always like, oh, when can we use this? But I think, you sort of covered this a bit when you talked about next steps, but it's really cool. I'd love to be able to start to share this with more people.
Do you, on kind of the training in different ways, do you guys think that, you mentioned like you could train it yourself on the WikiSQL data set. Do you think that that's kind of additive if you're talking about that versus, a customer or our own, these are queries and these are their titles? Like, do you expect that would be a fruitful source of, training data?
Well, that's an open question, right? We started with that hypothesis. It is fruitful to have trained on WikiSQL. However, some of the results suggest it may not have been, right? It may actually have been better to start from a pre-trained language model that is trained on the full corpus of, the web, as T5 has been, and go directly to the target task. So if we developed our own data set of customer SQL and titles, maybe going directly to that. But we haven't evaluated that.
Right.
How much training do you think would have to be like customer specific? Do we have any sense of like, do we see some broad trends, like maybe it's by industry, or I'm curious kind of what additional training we would have to do for particular customers.
Yeah, I mean, one of the challenges around language models, and this is sort of one of the questions I asked during the interviews for interns, is out of distribution vocabulary, because you start with a fixed vocabulary, and that vocabulary is very large. It's tens of thousands of tokens, or at least 10,000 tokens. But an individual customer might really want a particular token to be generated, and that it's doable. The models can't learn that on the fly, but it's better if they have more exposure to the domain of the task. That said, local retraining, if we have a centralized training system that deploys a decent model that is then further trained in the field, I would hope that that would also improve accuracy for individual customers.
Yeah, that makes sense.
Yeah. For that, you could like have a train a model more generally, just to be able to produce descriptions, and then fine tune, make a copy of that model, fine tune specifically for a particular industry, for example, which would take much less time than training that from scratch over again. Yeah.
And there are all sorts of interesting techniques, like you can add prefixes to the inputs to these models, and that can basically give a hint to the model that it should be doing one task versus another. So if you had a model that was trained on a task for SQL to English in finance versus SQL to English in medicine, you could have a unified model that was deployed and then given this task hint as part of its input. That's multitask models are still a research. Well, I shouldn't say they're still research. They're used in production in industry, but they're a little bit more challenging.
I think it might be like also unlikely that we would get that sort of data set, because I don't think our customers are going to, share their query text and their, table names and all of those things with us. So I don't think we would have multiple unified, corpus, like to train a finance model or whatnot. I think it would almost have to be general SQL out in the wild, and then more nuanced towards a customer specific stuff that we don't, we won't ever know.
Yeah, there is the upcoming HMC project may be able to give us the federated learning infrastructure to run the kind of experiments where we do. So we might know upfront that we are training on customer A. We don't know anything about their data, but we know some things about their company. So if we're doing training on their data blind, but we know that they're a medical institution, we might be able to experiment with hinting to the model based on that, or sort of presumptively labeling their data as more medical, or presumptively labeling other customers as more finance. That might be a mistake, that might not pan out, but it's something I've thought about. Cool. I just want to emphasize one thing, but while I have you guys here, just the incredible amount of effort that Aaron has put into this work, and the extraordinary skill demonstrated for someone who's still an undergrad. This is definitely graduate level work, and this task of taking a brand new data set, reversing it, and generating results that is novel, and I think he deserves a round of applause for all his work. Still got some training to do, but I was very, very pleased with this so far. And just so you guys know, Aaron will be sticking around until the 17th. So if there are further questions, there will be some additional work, and some of these next steps will be attempted. Please don't hesitate to reach out directly as well. All right, any last questions before we wrap up here? I know we had booked until 5:30, but I want to be respectful of everyone's time.
So that's awesome, Aaron. Did you have fun? Like, was this a fun and interesting project?
Yeah, definitely. This is pretty much exactly what I expected and what I've, wanted to do. So, I'm really excited to have had this opportunity and to use my deep learning and my machine learning, skills that I've learned in academia and kind of bring them over to Alation. So yeah, couldn't have asked for a better experience for sure.
Awesome. I hope we get to apply your work.
Awesome. Yep, here. Great job, Aaron, and I think we will. I think there's many applications of both directions you outlined today.
Cool. All right, well, thank you, everyone. I really appreciate your time. Thank you, Aaron. Again, I'll give everyone some time back. This recording will be made available to everyone in this group and those who are not able to attend. So look forward to seeing that in your inboxes soon.
Great.
Thank you.
Yeah,
All right.
good job.
Thanks, everybody. Bye-bye.
Thanks.